This is problem number 6 for problem set number 1. The ice caps of Greenland and Antarctica contain about 1.75% of the total water by mass on the Earth's surface. The oceans contain about 97.5%, and the other 0.75% is mainly groundwater. Suppose the ice caps, currently at an average temperature of about negative 30 degrees Celsius, somehow slid into the ocean and melted. What would be the resulting temperature decrease of the ocean? Assume that the average temperature of ocean water is currently 5 degrees Celsius. Okay, let's start with what is given to us, and that is the initial temperature of the ice caps. That is negative 30 degrees Celsius. It is also given that the initial temperature of the ocean water, is 5 degrees Celsius. Okay. And they also say that the ice caps contain about 1.75% of the total water by mass on the Earth's surface. And the oceans contain about 97.5%. Okay? So because they didn't give us the mass explicitly, let's make an assumption. And let M be the total mass of water on Earth surface. Okay. Therefore, the mass of the ice caps is equal to what it said, 0.75% of the total water on the Earth's surface, and oceans is 0.975, right? So therefore, the mass of the ice caps is 0.0175 m, with m being the total mass of water on the Earth's surface, okay? And the mass of ocean water is 0.975 m, okay? All right. What else is important to know in this problem? So this is a calorimetry problem, right? It's given to us right here. Let's take this graph up and bring it up. Okay, put it right there. So this is the graph for water, right? Water is a solid when it's below 0 degrees Celsius. It is a liquid when it is between 0 degrees Celsius and 100 degrees Celsius. And it becomes steam or a gas when it's above 100 degrees Celsius, right? Okay. We know that the initial temperature of the ice caps is at negative 30 degrees Celsius, right? We also know that somehow, suppose the ice caps, currently at an average temperature of about negative 30 degrees, somehow slid into the ocean and melted. So it's initially at negative 30 degrees Celsius and somehow it melted. So let's write that down, different color. Let's use green, okay? Let's say this is T initial temperature of the ice cap. And that is negative 30 degrees Celsius right here. Okay? So So initially, the ice cap is at a solid phase, right? So the ice cap experiences a solid phase. Right here, solid, that's for the ice. Okay, and then they also said that the ice cap somehow melts, right? Somehow slid into the ocean and melted. So it melts. This is for the ice. Okay. And then after the ice melts, it becomes water, right? So it ends up somewhere here in the liquid region. I don't know what the final temperature is. That's what we're trying to find out. But I know that it somehow ends up here in the liquid region. And that's just a little background, which we're going to use later because that's kind of important. Okay. So we also know that in calorimetry, right? In calorimetry, the sum of all heat transfer is 0. So in calorimetry, the sum of all heat transfer equals 0. Right? And that consists of two things, right? Consists of two things. The first one is a heat transfer due to a temperature change within the same phase. So that's Qi is equal to the mass times the specific heat times the change in temperature. Okay. And the other one is the heat transfer necessary to change phase. That is plus or minus the mass times the latent heat of fusion, or plus or minus mass times the latent heat of vaporization, right? For whatever material I we're using. That's just a variable for a random material, a random name for a random material. So let's just note that down. So this is heat transfer due to temperature change. Temperature change within the same phase. Okay? And this equation on the bottom is the heat transfer necessary to change phase. Okay? So this equation we use within the same phase. This equation we use when we experience a change in phase, right? And again, I'll repeat this. I've said this in the previous videos, but we use a latent heat of fusion when we go from solid to liquid or liquid to solid, and latent heat of vaporization when we go from liquid to gas or gas to liquid. Basically, when you go through the boiling phase change, then you use latent heat of vaporization, and when you go through melting, you use latent heat of vaporization. And plus or minus, it depends on when your system experiences, when it receives heat, when it gains heat, then we use plus, and minus when we lose heat. Okay, that's all that is. Let me just clear this up a little bit. Okay. So in our case, let us write our equation down. Our sum of all heat transfer equals 0 equation, right? So I'm going to start with ice, okay? I have the mass of ice This is for this part, the solid phase of ice, where it's within the same phase of solid. Okay, the mass of ice times the specific heat of ice times the change in temperature of ice, right? So that would be, for ice, if it's within this solid region, the final temperature of the solid region would be the melting point, which is T equals 0 degrees Celsius. So that would be 0 degrees Celsius as the final temperature minus the initial temperature, which we know here is negative 30 degrees Celsius. So minus negative 30 degrees Celsius. Okay. And then we also have this melting region, which is a phase change for ice, right? Because they said that somehow the ice somehow slid into the ocean and melted right there. So we're going to add that. So plus, because it melts from negative 30, we go up to 0 degrees. Heat is added into the ice in order for it to melt. So plus mass of ice. And in the melting region, like we said, we use latent heat of fusion, right? Because it goes from a solid to a liquid. Let me try to erase this thing. Hopefully. Yeah, there we go. Okay, so times latent heat of fusion for water. And then plus, and then plus the mass of ice. Again, the ice experiences a temperature change after it melts when it's in this region in purple, right? It's still in the same phase in purple because the ice melts and turns into liquid water. So we'll take that heat transfer due to the temperature change into consideration. So plus the mass of ice times this time the specific heat of ocean water, because the ice had melted, right, into liquid. So now it's in the ocean. And then times the change in temperature. So we don't know what the final temperature is right here for the ice, right? That's what we're trying to figure out. So minus TF, okay? But we do know the initial temperature right here. It's the start of the melting point. So that's 0 degrees Celsius right here, right? So minus 0 degrees Celsius. All right, because we don't know what temperature this is, that's TF. But we do know that right here, it's 0 degrees Celsius, right when it melts. Okay, so then we add, this time for the ocean water. The ocean water doesn't experience a phase change because it was already water, it's liquid, and it stays liquid. So we just use the formula for the heat transfer due to temperature change within the same phase, right? It stays as a liquid. So plus mass of ocean water times specific heat of ocean water multiplied by the change in temperature, which we don't know what the final temperature is, so we'll call TF. But we do know what the initial temperature is of the water. It was given at 5 degrees Celsius right there. So minus 5 degrees Celsius. Okay? And that equals 0, right? All that equals 0. And let's try to separate this into categories, just so it's clear. Okay? So this part of the equation is the heat transfer due to temperature change for ice within the solid phase only, right? The solid phase only. Before it melts, basically. Before it melts. Okay? And I'll try to use the same highlighter color, just so, there, I think I used orange. Is that orange? Yeah, that is orange. Okay, so this guy is for this guy right here. That's heat transfer due to temperature change for ice before it melts, when it's still in the solid region, okay? And then this equation right here, this part of the equation, is for the heat transfer of ice necessary to change phase when it melts. So that guy corresponds to the melting part right here. So that is heat transfer for ice necessary to change phase when it melts, right? I'll write that down, just since it's a video, you could skip ahead if you already know this. So this is heat transfer for ice necessary to change phase. Basically when it melts. Okay? All right, this part of the equation is the heat transfer for ice due to temperature change. Due to temperature change within the liquid phase only. Or after it melts. Right? And that is, I think I used this one, right? Yeah, that is this part of the, after the melting point, that's this guy right here. So this part of the equation corresponds to the liquid phase, after the ice melts and is liquid. Okay? And lastly, this part of the equation right here, that is the heat transfer for ocean water. So that's the heat transfer for ocean water. I'll call it OW. Due to temperature change within the same phase. Within the same phase. Okay? And we know that the ocean water was at 5 degrees Celsius and it was just a liquid, right? It did not change phase, so liquid only. So for that reason, the ocean water part doesn't have this formula, which is the heat transfer necessary to change phase. It doesn't have that because it stayed as a liquid. Okay? And all that is right here equal to 0. I ran out of space, but it says right here equal to 0, right? Okay. So let's see, I am looking for, what I want to find is this guy, TF, right? So I'm just going to rearrange my equation to find TF at this point. Okay? And so I've got, also I'll cancel out, because I have 0 degrees Celsius, this goes to 0. I guess I shouldn't use red since I've already used that. Let's use pink. That goes to 0 and that goes to 0, right? So I've got mass of ice times specific heat of ice. This is, we've got a minus negative 30, so that becomes positive. So times positive 30 degrees Celsius. Okay, and that is plus the mass of ice caps, sorry, I've been saying ice, I meant to say ice caps, times the latent heat of fusion for water, plus the mass of ice caps times the specific heat of the ocean water, multiplied by the final temperature, so times T final, that's what I'm looking for, plus mass of ocean water, specific heat of ocean water, times final temperature, and then minus mass of ocean water, specific heat of ocean water, times 5 degrees Celsius, right? And that all equals 0. 0. Okay. I'm just gonna rearrange that and put all these terms with TF on one side of the equation, just to make it easy for me to solve. So I'm gonna have the mass of ice caps times specific heat of ocean water times final temperature, plus the mass of ocean water times specific heat of ocean water times the final temperature, is equal to the mass of the ocean water times specific heat of the ocean water times 5 degrees Celsius minus mass of the ice caps times specific heat of the ice caps times 30 degrees Celsius minus mass of ice caps times the latent heat of fusion for water. Okay? And then if I factor out the final temperature on the left side of the equation, I will have TF, right, is equal to all of this divided by, or I'll just write it down, times the mass of ocean water, specific heat of ocean water, times 5 degrees Celsius, minus mass of ice caps, times specific heat of ice caps, times 30 degrees Celsius, minus mass of ice caps, times the latent heat of fusion for water, divided by mass of ice caps, specific heat of ocean water, plus mass of ocean water times specific heat of ocean water. Okay? And let's see. A lot of these are already given, right? What color should I use this time? Let's use this one, I guess. So I know the mass of ocean water. I know the mass of ice caps. I know mass of ice caps, mass of ocean water, mass ice caps. These are just numbers, so that's given. So I am looking for the latent heat of fusion for water, specific heat of ice caps, and specific heat of water. Okay? And I found that on Google. So that the values for those guys, according to Google, again, on a test, this is going to likely be given to you guys. But the specific heat of the ice caps value is 2,100 joules per kilogram times Kelvin. The specific heat for ocean water is 4,190 joules per kilogram Kelvin. And the latent heat for fusion of water is equal to 3.34 times 10 to the 5 joules per kilogram. Okay. So now I know all the values on the right side of the equation, and I can just at this point plug it in my calculator and get the final temperature. Okay. So when I plug that in, I'm gonna get TF is equal to, actually I'm gonna move it a little to the left because I don't have a lot of space. So TF is equal to 0.975 M times 4,190 joules per kilogram times Kelvin times 5 degrees Celsius, okay, minus 0.0175 M times 2,100 joules per kilogram Kelvin times 30 degrees Celsius minus 0.0175 M times, I'm going to move these guys out of the way. Okay, make them smaller and move them out of the way right there. Okay, times 3.34 times 10 to the 5th joules per kilogram. And I'm going to divide all of those by 0.10175 M times 4,190 joules per kilogram Kelvin plus 0.975 M multiplied by 4,190 joules per kilogram times Kelvin. All right. And if you guys notice, each term has an M, right? So we could cancel those out. They cancel each other out. The top M and the bottom M cancel each other out, okay? So cancel, 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 cancel. Okay. So if I plug all those values in my calculator, I am going to end up with 13,478.75 divided by 4,158.575, which is equal to 3.2412 degrees Celsius. So the final temperature is equal to 3.24 degrees Celsius. Okay? But that's not what the question was asking for, right? The question was asking for what would be the resulting temperature decrease of the ocean. So that means the initial temperature of the ocean water was, assume the average temperature of ocean water is 5 degrees Celsius. So we have, actually we wrote it down. Yeah, here, see the initial temperature of ocean water is 5 degrees Celsius. So what we'll have is the initial temperature of ocean water minus the final temperature is equal to, what was the question? The temperature difference of the ocean, right? And that is equal to initial temperature of ocean water is 5 degrees Celsius minus TF, which is 3.24 degrees Celsius. So therefore, and that's equal to 1.76 degrees Celsius. Therefore, the resulting temperature decrease of the ocean would be 1.76 degrees Celsius. So that's our final answer. Okay, hopefully that helped, and hopefully you guys understood why the different phases of ice, right? From solid to the melting to the liquid, and why we had to have three categories for ice. So before it melts, during melting, and after melting. All right, hope that helped.